Alright, welcome back. Let's finish this. Let us get to where we left off. Stopped with the heap. Now on to the newer stuff, and there aren't as many things, honestly, so we're almost there. So what I want to talk about first is searching, and as the name implies, you are looking for something. In this class, we've mostly been talking about vectors, so vectors and arrays. But when you take CSCI 41, if you do, you'll learn many more other data structures, and you can think about searching through those as well. So searching is something we can do in an array or a vector. We have something we want, and we have the vector itself. So for example, we want to look for, I don't know, here's our vector v, it holds 8, 6, 7 or something, and you can ask this vector like, hey, search for 6, and it should give you back the index at which 6 exists. So it's like, yeah, 1. Or you'd be like, where is 5? And then it'll be like, nowhere. Okay, that's the idea. That's what searching does. It'll give you back the index of the thing you're looking for. And so linear search is super simple. It's just go through the entire thing from left to right, looking for this thing you're looking for, and return back the index if you find it. Okay, that's all it means to search linearly. You're going from left to right or right to left. Usually it's left to right. And you're just returning the first thing that you see. Like maybe there are 2 6s over here, but you want to find the first one. Okay? That's what linear search can give you. All right. So, and then you'll give back the index of the value if you find it, and some other way of saying I didn't find it otherwise. Usually it's like -1. Okay. So linear search is nice, and you are forced to use linear search when your array isn't special. Okay, so linear search always works because you're looking at everything. But you can imagine it's quite slow if your vector is giant. So going from left to right, looking at all the indices in like in a million length vector, that is a horrible time. That will take a while. So there's ways to do it better if you have some guarantees about how the vector looks, how the array looks. So it works no matter what the vector slash array looks like. It'll find it if it's there. It's looking at everything. Binary search, on the other hand, exploits the properties of special arrays, okay? It exploits the order of elements in a sorted array. Okay, so if an array is sorted, we have some very strong guarantees about where things are. Every index less than maybe index I has smaller things. And every index greater than index I has bigger things. So here's my sample vector. I don't know. 2, 4, 6, 8, 10. So here's my index I. Ah, yes, everything's smaller. Every index smaller than I has smaller things, smaller than 6. Every index bigger than I has larger things, larger than 6. So if you're looking for something, and you guess that it might be in at index I, you know where to find it if it's not the thing you were looking for. So it's like if I was looking for 10 and I saw the 6, I know I need to search this way. Otherwise, if I were looking for the 2 and I saw the 6, I need to search this way. So you can always cut off half the array each time you look inside of things, if you do it right. Okay? Yeah. So, each time you observe a value, you can cut off half the array each time, assuming you keep looking in the middle, okay? Start your search in the middle of your search space. That's the key. And for my coding example, we're going to code up binary search together. Okay, so let's get right into it. Let's code it up. Okay, so I have my vector. It's 10, it has to be sorted for binary search to work, otherwise we don't have guarantees about where things are. And then we want to say, I don't know, let's find the 2. V2, let's also find the, I don't know, the 10, the 6 would be nice. We can find all of the things. Doesn't really matter. Let's find something that's not there. Let's look for 5. Let's look for 5. So we know what we want to get back. We want to get back 0. We want to get back index 4. We want to get back here index 2. We want to get back -1 because it's not there for that one. Okay? That's the idea. And now we'll go and implement binary search. I guess we might as well print these out, huh? Let's see here. What do I want? I want to record a macro. Let's go here, insert cout, then let's find the semicolon, insert a new line, and go down. Okay, the magic of Vim, I can repeat that process. Okay, now int binary search, because it's going to return back the index. It's going to take a vector by constant reference, because we know how good that is now. We're not copying things, we're not touching things. And then int val to search for. Okay, and so either we're going to find it or we're not going to find it, and let's figure out how we're going to do this. So again, we always want to make a guess. We want to make a bunch of different guesses. And the first one is in the middle. Okay, so we're going to guess in the middle. We're going to guess the middle index. So v.size is 5 in our case. Then our middle index is originally, and we don't know where this thing is. It could be over here, it could be over here. We don't know what the array looks like. We just know it's sorted. So our search space starts here. This is our low index. This is our high index. And our mid is in between. It's 0. 0 plus 5 over 2, integer division. That's going to be 2, index 2. Okay, index 2. There it goes. And that's essentially where we want to be. And then we will search for the value that we're searching for by starting in the middle. Okay, so we're going to look at mid, see what it is, and therefore, and after we've seen what it is, we can chop off part of the array. Either it was too small or it was too large, and we need to look over here now. Okay, so that is the idea with that, and the first thing that we're going to search for is going to be the 2, so let's walk through how it's going to work. Okay, so the val that we're searching for is 2, and let us walk through exactly how this is going to execute now. So we want to search for 2, and we see 6. That's no fun. That means, though, that our guess of where it should be, the midpoint of our search space, was too high. Okay, so that means that everything that we need to be looking at is all the places to the left of the midpoint. You see that? So the mid wasn't the value, so obviously we don't have to look at that ever again. But now we are going to change our high index. Okay, the high index, if we guessed and we found a number too big, the high index needs to change. So it's going to go from there to now right here. You see that? So the low is 0, index 0, and the high is index 1 now. And we're looking for 2, remember. So then we will search, we will guess the midpoint of this space now. So the midpoint of that is 0 plus 1 divided by 2. Integer division is index 0. And hey, we found our 2. Okay. That is exactly how this is going to work. And that's what we'll be coding up. So just keep on having our search space cutting off the side that we don't care about, because we know we're never going to find that thing over there. All right, so we're going to get our midpoint, set our low and our high. Originally, our search space is everywhere, so the low is index 0, because it might be in index 0, and then the high is v.size minus 1, because it might be over there too. So we got to look everywhere, and then we start our mid. Okay, so int mid equals low plus high over 2. And then we'll have a while loop. So while we haven't found the thing, while something is something, we'll get there, we're going to see where we are and cut off half our search space. So if v at mid is, well, what was this case? V at mid was too big, okay? V dot mid was bigger than the value that I was searching for. In that case, we need to cut off the right half. Search to the left. That's the idea. What we saw was too big, so we know we need to search in the left half of this array. So the new high is now mid minus 1. You see that? And then the other case is symmetric. We found a value that was too small. We need to look in the bigger half. Okay, search in the right half. And then high equals mid, then low equals mid plus 1, because we knew it wasn't the mid. And this should be an else if. Only one of these 3 cases that we're about to show will ever happen. Else, we found it. Okay, if it's not less than, it's not greater than, it's equal to. And we can return the index. The index is sitting in mid. Okay. Okay. And then we're going to keep on doing this over and over and over again, calculating our new midpoint. Things like that. Actually, you know what we can do? So we can calculate the midpoint at the very beginning. I'll bring this in here. That works. And then the secret condition that you need here is while your search space is still non-empty. So some non-empty search spaces are like, all right, low is 4 and high is 6. It's somewhere in between index 4 and index 6. Again, a non-empty search space is like low 5, high 5. It's like, okay, if it's there, it's in between index 5 and index 5. So it's hopefully index 5, otherwise it's not there. An empty search space will eventually have it where low passes high, where they swap places. And that means it's empty. Okay? I'll give you an example of that happening. But the correct case here is while low is less than or equal to high, while the search space is not empty. Do things. And then if you got past here and you didn't return, it wasn't there. You didn't find it, and then you'll just return -1. Okay, so let's watch this work, in theory, if I didn't make a silly mistake. Cool. Is that what we wanted? Yeah, it was. Cool. Why does this make sense? Let me show you the example. Let's pretend we were looking for not 2 but 3. So we would have gotten this far. Oops. I want to duplicate this slide, please. So let's pretend the value that we were looking for was 3. We would have gotten to the same spot. Value we're looking for is 3, not 2. And so we looked at index 6, we looked at index 2, it wasn't there. So now, it's not at index 2. So the number that we're looking at, like we looked at the 6, it was too big. We looked at the 2, it was too small. So we got to cut off this half. It must be in between index 1 and index 1. Yeah, so we changed low again, or we changed low for once to now be index 1. And so the new mid is, well, the mid was, sorry, the second mid was index 0. Let's go back to that so that you have an idea of where we came from. I'll actually put that there too. The second mid was 0. That was the right one for that one. And now our third mid is going to be in between low and high, which are, well, that's index 1. Because they're both 1. Low is 1, mid is 1. Okay. Finally, mid is 1. And we're looking at 4. Okay, it's too big. We have to go this side. And so when it's too big, remember what happens. We need to search the left half. We say high equals mid minus 1. So now high, if I bring in the rainbow, high is mid minus 1 now. So high is now 0. And low is still 1. Okay, so at the very end, high equals 0, low equals 1. What? That means our search space is empty. Okay? They passed each other. You didn't find the thing. Okay, hopefully that makes sense as to why this is the correct condition for determining whether or not the search space is empty or non-empty. Okay, so that's searching, that's binary search. Linear search, I trust that you can implement. Recursion is the next topic, and I got some fun ones for you. So if we go to our handy-dandy cheat sheet, I've made you a page for it. Recursion is all about finding a problem inside of itself. Okay, remember that. It's where you solve a problem in terms of itself. And the smaller versions is key. Okay, smaller versions of itself. And going through this example, the factorial, we find that, oh yes, we will find the smaller factorial inside a bigger factorial. Okay, so the steps for coming up with a recursive solution are always the same. You always first write out an example to see how it's working, see if you can find the problem inside of itself, and then you do it. And then you make a leap of faith. You assume that the recursive call always works. And then you make the recursive case of your algorithm by generalizing this case that you found. Okay, change 5 to n. Okay, what is it? What's the real answer now? N times p of n minus 1. Okay, then you keep trying it out until you find a nice stopping condition. There might be a bunch. And those become your base cases. That tells you when your recursion stops. Okay, that's why you want it to always make it a smaller value, so eventually you get to the base case. And then keep trying examples until you're happy and you think that it's the right answer. That is essentially recursion in a nutshell. That's how you come up with a solution for recursive problems. So let's do the power example, x to the n. So like 2 to the 3 is going to be, well, that's 2 times 2 times 2. Do I find a smaller power computation inside of this? Yes, I do. That's 2 squared. So now we generalize. Okay, 2 to the n. That is 2, or honestly, m to the n is m times m to the n minus 1. Okay? And that is our generalized recursive case. This is rec case. And then, my cat is going crazy right now, sorry. Then we're going to try this out. Like, okay, try this out on 2 to the 3 and see what happens. Okay, 2 to the 3 equals 2 times 2 squared. Okay, recursive case again, that's 2 times 2 to the 1. Okay, that makes sense still. That's going to be recursive case again. 2 times 2 to the 0. That actually still makes sense. Okay, 2 to the 0 is going to be 2 times 2 to the minus... Oh. 2 to the minus 1. I mean, that comes out to being 1, but that seems kind of useless. Let's go even farther. What's 2 to the minus 1? 2 times 2 to the minus 2. That's just 1 again. This is kind of useless. We're already multiplying by 1 here. So we found a stopping condition. It's like, oh, 2 to the minus 1. That's kind of weird. What? So that weird case is where your recursive case breaks down, and that's where you want to stop. You're like, okay, it's 1 when you get anything to the 0 power. Okay? That's your base case. Base case is m to the 0 equals 1. And then we've solved the problem. Okay, and you can convince yourself that it works by trying it out with different values, but that's how we do it. It's recursive in the power. So m stays the same. All right. So recursion.cpp, I guess. So we'll say cout pow 2 to the 3. Let's say pow recursive, because I know there's a C++ library function called pow. Double pow recursive. You can take a double first parameter, m, but the next parameter needs to be an int to the power of n. Okay? And here we go. It's going to be, if we're in the base case, if n is 0, return 1, else return. The answer in the recursive case is, well, it's m times m to the n minus 1, which is pow recursive m n minus 1. Yeah, so we just kind of read off what we found. And hopefully that's making some sense. So that's the first example, and let's watch it work. It should give us back 8. No. Oops, yeah, sorry. We want to output as a recursion, not recursion.cpp. Cool. So it's going to work as long as the number that you give is initially is non-zero or non-negative. My example 2 is recursive binary search. In fact, you can do binary search recursively. And let me show you that. So the way that it'll work is you just keep low and high as parameters. Okay? And you'll just watch it change. So if it makes more sense typing it up, but it'll be like binary search v, and then you immediately give like your low and your high as parameters. Okay, that's the idea. So let me show you that. You know what? I can copy a lot from over here. Whee! This is going to be binary search recursive, though. So it's all very similar. A lot of this is going to be the same, but it's not going to be quite the same. Whee! So we also need a value to search for. The val. And then we'll just pass along low and high. And this is going to be an interesting case of recursion, but it's going to make sense. Recursive calls will get smaller. Int low, int high. A smaller recursive call to binary search is when the absolute value of high minus low, or I guess high minus low, yeah, absolute value, gets smaller. Okay? So when the distance between high and low is smaller, that counts as a smaller recursive call. All right? That's the idea. And then what are your base cases? When do you immediately know the answer? When the search space is empty or of size 1. So you can say if your search space happens to be empty, if low is greater than high, then we'll return -1, it's not there. Otherwise, else if low is equal to high, it better be in that one place, so we'll check if it's there. If v at low, for example, they're all the same, is equal to the value to search for, then you can return low, else return -1. It's not there, you didn't find it, because this is your one thing in your search space, low equals high. Otherwise, we have a recursive case. And in the recursive case, we need to check, like, where are we? We need to find the mid now, equals low plus high over 2. Then we need to check the mid and see if v at mid is, again, less than, greater than. If it's greater than the value that I'm looking for, I need to look in the left half. Else, and then I'll do another if it's greater than, or it's smaller. We'll look in the right half. Else we found it. Return that index. And here's where we make our recursive calls. This is a very fancy example. I think your book has an example of this, so I won't explain it too much, but this is where we make the recursive calls. So we need to look in the left half. We need to eventually return the index of where this thing is, or -1. So we have to return something here. We have to say return. And the result of returning, well, what is that thing? We need to look in the left half. So it's just binary search. If we find this, it's going to be somewhere in the same V, searching for the same value, from low to mid -1. That's how we change low and high now. We change them in the recursive calls. It's like the result of this now is whatever this is, and it's a smaller recursive call. It looks in the left half, because low and high got smaller. You see that? That's awesome. That's beautiful. And I do encourage you to read your book's explanation of all this stuff. I don't have enough time to talk about it. Otherwise, we're going to say mid +1 and high. And then we found it otherwise. Okay. And I didn't include vectors. That's why it was yelling at me. Okay. Dun dun dun. And so now when we call this function, we can make a helper function that just does this for us, but we need to give low and high initially. 0 and 5. It's all of these. Oh wait, is it 4? 0, 1, 2, 3, 4, sorry. It is 4. There we go. Let's try it. 0, 4, 2, -1. Awesome. So I do encourage you to read the way your book explains this, or stare at this code to understand why the recursive case looks the way it does. Okay? Why there are 2 base cases, things like that. But that's a good example, I think. So that's all I got for you for recursion. Up next is makefiles. So let's talk about compilation very quickly, just so that we remember what's going on, and we'll go from there. So when you have, if you remember this very, very small version of the same picture, remember that if you have a C++ program, you're going to give it to G++, but G++ secretly does 2 things. It compiles and it links. It's sad that it does this, but you don't really get to see the difference when you're starting out programming. Okay, but we have discovered the difference. So the idea is G++-C is the compiler, and then G++ with like a -O saying, I want this to be called an executable file exec or something. That is the linking process. So let's see here. Let's pretend you have two files, a.cpp and b.cpp. We can compile those, and compilation just means, I guess I don't need this. Compilation just means taking a single source file. Yeah, don't know why I'm on caps lock, sorry. Taking a single source file and turning that one file into machine code. That is the compilation process from C++'s point of view. So a.cpp will turn into a.o, that is an A, and b.cpp will turn into b.o, which those are the ones and zeros, whereas this is like the text. You got your includes and things. All right, so that is the compilation process. You see, you do g++-c and then the name of those files. And then you can link them together in the very end into like a program called main or something. And that's again binary, but it includes a.o and b.o linked together. And also maybe like the, I don't know, IOStream library. That's in a binary file somewhere as well. The linking process, g++-o, with other things of course, g++a.o and b.o -o main or something, that brings them all together into your final executable called main. So linking takes compiled things and combines them into one final executable program. An executable program is just a single file that you can run on your computer now. Okay. The compiled code is not good enough to run because you're probably going to be using library files. Be like, oh, I need to call cout over here. Cout needs to happen in here, and then maybe I need cin in this file. So you can't run any of them without linking with IOStream. You have to wait. You have to wait until the linking stage. So G++ can do it automatically. G++ can compile and link if you give it a C++ file and just say -o. But we can also do separate compilation. And remember what that means. That means going through those intermediate.o files. And those are the compiled files. Okay, and then linking them together at the very end. And what you get out of that is that you only need to end up recompiling what's changed. If you touch a.cpp, then you have to recompile it into a.o again. But if you don't touch b.cpp at the same time, you can keep the old one and just link with that again. It didn't change. That's the beauty of separate compilation. And that's just like take those steps. Use the -c and then the -o with the .o files. a.o, b.o, things like that. Okay. So a makefile, after all that, a makefile just gives you a bunch of recipes for how to build things in whatever order you want, with whatever intermediate files you want. It's more than just for C++ programs. It's for any terminal command you want to just like put together. For any file that you could possibly make, you can make a makefile to make that thing. But we like to use it for our programs. So a makefile tells G++ how to build things, and there's always, you got your targets, remember your targets, your requirements, and then your rules, your actual terminal commands. That go and execute and make something. So this is a lot of words, some weird looking diagrams. Let's go to your cheat sheet. So I'm kind of out of order, sorry. Makefiles. Let's pretend we have a.cpp, b.cpp, and b.h. Again, we don't ever compile the .h files, but it's coming along for the ride. So a.cpp has the main function and includes b.h, for example, we will use separate compilation to compile both of them. Okay, so we first make A.O and B.O, and then we'll compile that program into these together. We'll link them together, A.O and B.O, into a program called prog. Okay, so here's what you do in a makefile. You say how to make A.O first. I mean, these can be in any order, but we'll say how to make A.O first. That's the target. That's what we're making. We require A.cpp to make A.O, so we're going to put that after the colon. And then we say the terminal commands, that's the body of the rule, we give the terminal commands to go and make A.O using the requirements. That is a makefile rule in a nutshell. And so we do the same for B.O, and then when we want to make this thing called prog, we just say that, oh, we require A.O and B.O. And that is the magic of makefiles, because if some of those dependencies, like A.O and B.O, those don't exist, and you say make prog, it'll go and make them for you. It'll run these rules and then be like, oh, okay, now I'm ready. Now I'm ready to do the body of this rule that you really wanted. Okay, that's the beauty of makefiles. And do take a look at all this on your own time. But let's use these concepts now to just compile a library using separate compilation. Let's make a very simple library. Be like, do I want to reuse any of this? Maybe, maybe not. Let's just say make a new folder for my makefile example. So I made that folder. Let's cd into it. There's nothing there right now. Let's make our own A.cpp and B.cpp and B.h. Okay, so here's our main function. Let's say, I don't know, the function that B.cpp defines and B.h declares is like foo. Let's see how foo of 42 or something. Okay, so then we're going to say in B.h, okay, that's where the foo function exists. So let's make a B.h file. Remember your header file guards to keep from infinite inclusion. And we'll be like, okay, foo is a function that returns in it and takes in it. Yeah. And then B.cpp will include B.h and then define foo, and let's just have it, I don't know, return x plus 1. And so now I've got a nice little family of functions and files. A.cpp calls foo, which is declared in B.h and is defined in B.cpp. Okay, hopefully that's not too bad. Yeah, try again. I've made the file since then. Okay, so we have all those files. Let's compile them using makefiles now. Okay, we make a file that is called makefile with a capital M, and then we give our rules. So we can give them in any order. We can say prog first if we want. Or maybe we can call it main. Why not? To make a file called main, we need A.O and B.O. And once we have them, we can say G++ standard equals C++17 as usual, A.O and B.O, -o main, because that will make now an executable file called main, which is the name of the role. That's what we wanted. And then for A.O, in order to make that, we require A.cpp, and we'll use G++ with all this stuff, and then a -c, and then an A.cpp. Okay, that's how we make A.O, and then we'll do the same for B.O. Yeah, so now we can say like make A.O if we wanted to, and run the one rule that makes A.O. It'll run this as it did. And now we have A.O, or if I get rid of it just quickly, I can say make main, and it will make the main file. It'll run these rules, intermediate rules, to make A.O and B.O, because it knows that it needs them and doesn't already have them, and then it'll compile them into main, which we can then run. Beautiful, huh? So the beauty of this is that if one thing changes, or one thing's already compiled, you don't need to recompile the other, as you would have if you just did G++ standard equals C++17, A.cpp, B.cpp, -o main. This would have to recompile b.cpp as well. No fun. So let me remove b.o and say make main again. Now all it needs to recompile is b.o. a.o is already here. We already have it. It's already right there. And now we have main again. Okay. So, I think that's essentially all I want to say. You are now experts in makefiles. Let's move on. The next thing is bitwise operations, which are very fresh in your mind, so I don't have to say too much here. Here are some examples of each of them. So you got your AND, you got your OR. Remember that ints are 32 bits long. Whee. Remember that ints are 32 bits long, and therefore you have 32 ones and zeros, not just the 8 that I'm giving as examples. Just remember that. Bitwise AND does an AND on all the bits. Bitwise OR does an OR on all the bits, where 1 and 0 is now 1. Bitwise NOT flips all the bits. Then you have your shifts left and right, which adds some zeros, or like on one side or another, and you can remove from one end and add zeros to the other. And XOR is exclusive, or that's only ever true if both of them are different. So 1 0 or 0 1 produces a 1. That's a true, but not true true is now false. Unlike regular OR, false false is still false though. Okay, so that's the bitwise operations. I guess I don't need to put all of them like this. Bitwise operations perform logical operations on individual bits of numbers. Usually 2 numbers. NOT only takes a single number and it inverts all the bits. But the rest of these take 2 numbers, and then shift is also a bit different in that it takes an integer, like how many bits do you want to shift by. Okay? Logical operations on the bits of usually 2 numbers. Okay, I guess I'll do this. We can just keep them all on the same line, maybe. Remember, we have left shift and right shift, and remember that AND is good for checking bits, OR is good for good for setting bits, and XOR is good for flipping bits. Okay, so let's implement both of these. Multiply by 2 to the n and flip bit. Bitwise.cbp. Oops, I didn't really copy now, did it? There we go. So this will be give back an int. This will be give back an int with the flipped bit. So let's do it like this. You remember that 1111 is 15. Let's flip bit 2 of 1111. So we'll say cout flip bit 15, and we want to flip bit number 2, which should produce in binary 1011, because it started out being 11111, and then we were going to flip this one right here, bit number 2, and that becomes 8 plus 2 plus 1, which is 11. 11 base 10. So that should give us back 11. That's what flip bit can do. And then multiply by 2 to the n makes sense. That's like multiply by 2 to the n. We take a number like, I don't know, 3 and multiply that by 8. That should, oh sorry, multiply by 2 to the 3, which is 8. So that should give us back 3 times 2 to the 3, which is 24. And we can use bitwise operations to do both of these, is my claim. So to multiply something by 2 to the n, we can use shifting. Because you shift a number, if you shift a number left by 1, that multiplies it by 2, because it adds a 0 at the end in binary. Which is just multiplying by 2. Similarly, x shifted by 2 bits multiplies by 4, because it adds 2 zeros at the end in the binary representation. So that's 4, multiplies by 4. And then 3, for example, multiplies by 8. So I hope you see where I'm going with this. We can just shift by that amount. Shift by n. And suddenly we've multiplied by 2 to the n. Isn't that fun? And so let me just return negative 42 for this one and make it a stub for now. Oops. We do in fact get back 24 for the first one, and now let's work on this one. To flip a bit, we can just flip a bit. We can XOR by 1 to the which bit, because that will put a 1 in that bit position. Okay, we'll just XOR to flip a bit, because, for example, 1111 XOR 0, 1, 0, 0, that gives us back, well, what's 1 XOR 0? I'm looking at the first digit of both, 0 and 1. Well, that is going to be a 1. It's going to keep it. And when there's a 1 now, we're going to flip it, because if it is a 1, now it's going to be a 0. Okay, so 1 and 1 make a 0. So we flipped that bit, and the rest of these likewise. 1 and 0 make 0, or sorry, they make 1 and then 1. So we keep those. So this one here just flips it. It flips that bit only in that position. Because the rest of these zeros will make 1s if they were 1s, or 0s if they were 0s. So they'll keep those other bits just as they were. So all we have to do, return, let's see here. I guess technically I can also return an unsigned int. Why not? Return x XOR'd with 1 to the which bit do I want to flip. So in our case, it's going to be 1 to the 2, which is going to make, in binary, 1, 0, 0, which is exactly what we wanted here. We wanted it to be this number right here. Okay? So that's flipping of bits, and in theory we should get back 11. Hey, okay. I'm happy with that. That's your bitwise operations, and finally, the last thing is exceptions. So exceptions are just a different way of alerting that an error has happened. And you can, for example, there are runtime errors in standard except. Take a look at that if you want to remember. What you do is you try to execute code that might throw an exception. And then you catch exceptions you know how to handle by reference and handle it. Okay? And that's the idea. If something bad ever happens, you throw that thing. Okay, that's all you need to worry about for exceptions. Let's see, do I say anything up here about them? Yes. So when something bad happens, you can throw an exception, and when you want to execute code that might throw an exception, you wrap it around in a try block somewhere. You can have multiple try blocks inside of try blocks, inside of function calls, whatever you want. C++ remembers the order of which catch blocks can handle which exceptions, and they can override each other as well. The closer ones get called. So a catch block is going to say, like, hey, I know how to handle a runtime error. Hey, I know how to handle maybe like a string or something if you were to throw a string. And for any standard library exception, like runtime error, things like that, there is a .what method that you can call, and that gives a string back to tell you what went wrong. Okay? All right. So to our last example now. Last two examples. Let's have recursive power that throws an error when it's a negative argument. So normally that wouldn't work. It would give me infinite recursion, but we're going to fix it. So I have very, very wisely chosen things that we've already written. So let's go back now to, hey, reload. Oh, I never saved the file, did I? No. Darn. Okay. I have frozen my thing, it seems. There it goes. Now it's happy. Okay. We've got power recursive now, and then also I want our bit flipping stuff. So where's that? Flip a bit. Because which bit might be bigger than 31? Because the user is silly. If that ever happened, we also want to throw an exception. So, for ints, there are only bits 0 through bit, there are only bit 0 through bit 31. There's 32 bits. So if the user gives us a silly one, like if which bit is greater than 31 or it's less than 0, then we're going to throw a runtime error. Same for power recursive. If we ever get an n that is negative, that would give us runaway recursion, and we don't like that. So if n is less than 0, throw another runtime error. Can't handle negative exponents. Okay, so now in main, we can make the bad calls. We can say power recursive 3 to the negative 2. We can say flip bit 15, flip bit 33. And these are going to throw exceptions now. Bam. We get a runtime error, can't handle negative exponents, and actually that caused the program to end because we didn't handle that exception. If we want to handle the exception, we have to wrap it in a try-catch. Okay. So we'll say try to do something that might throw an exception, catch the type of exception that it might throw. By reference, we usually catch things by reference, and then we'll say uh-oh, something happened, and then we can say like e.what, and the program won't end, but we will have caught the error in theory. And maybe we'll fix it. Maybe we'll be like, okay, the answer is 0 or something in that case. Okay, same for the other one. Now they're both going to fail, but we'll catch them, and so the program will continue because we caught the error and handled it. Okay. No, and I forgot new lines. There we go. Can't handle negative exceptions, and how dare you. So obviously you need something more involved in these catch blocks, but this is good enough for our purposes at the moment. So yeah, just throw in, literally, exceptions in all the places where things can go wrong. You can throw any type. Usually we use one from standard except, like runtime error. But you can make your own, as well as throw any class that you want to throw. Okay, so that's exceptions. You are now exception experts. And that brings us to the end of this review, and therefore the end of this class. So thank you for putting up with me. It's been a wild ride, and we are all now prepared for the final, I think. Here are the last memes that I have for you. Good luck, you're going to do great, and please come to office hours if you have any questions about anything. Obviously I can't teach or review in the final everything that may be bugging you, so please come to office hours for the last week, and let's get everything that is a bit fuzzy in your mind perfectly concrete. So I hope to see you there, and if not, I will see you in the final. All right, see you then.